Today's video is about flip-flops, and we're going to introduce the first most basic flip-flop, which is the RS flip-flop. So combinational circuits, as we know, are made up of logic gates. Logic gates are the basic building block behind all of those circuits. But what we probably don't think about when we're making them is the output of those circuits always depends on what that present input is. And we're going to find out later when we look at sequential circuits that that's different. So some examples of the ones we've made: grade 10 we made some adders, subtractors we made in grade 11, and decoders is another example of a combinational circuit. In addition to all of the other circuits that we simplified during the Boolean simplification of those SOPs, which are the sum of products equations. So getting on to sequential circuits, well, the flip-flop is the basic building block behind combinational circuits, and flip-flops are actually made from logic gates. The output is different with sequential circuits in that it depends on some previous input and the present input. And we'll explain that and get into detail about what that really means, but it forms the basis of what we know to be memory circuits and shift registers, counters, and a lot of other useful types of circuits. But more importantly than anything is the concept of this idea of storage. Okay, and you can see just from the look of this flip-flop circuit here how that feedback is present. So an example of a sequential circuit that we have here is a calculator, which is an example of a shift register, which is a type of sequential circuit which is made from flip-flops. So if I wanted to press the number 6 on the keypad, okay, I wouldn't have any difficulties doing that. The 6 would pop up there. But then if I wanted to press another number, like for example the number 7, what would happen to that 6? Well, we'd have to store that somewhere so that we could then insert the 7 in place of the 6 and then shift the 6 over like so. Okay, so that shift takes place as a result of the ability to have a place to store it. Again, if I add the number 2 on that keypad, the 6 and the 7, they have to be stored, and likewise they get shifted over to the left to make room for a 2, and that just continues on like that. So important characteristics to note about these shift registers: they have memory characteristics because they have to hold those numbers somewhere before they get shifted. Okay, and then the shifting property itself is actually a characteristic of a shift register, hence the name shift register. Okay, looking at sequential versus combinational, another example which really stands the test of time here is the calculator example, but when we add two numbers you can see the difference between those two types of circuits. So the first number entered would be 9, and we know that it's going to be stored in the circuit because that 9, when we press the plus sign, has to go somewhere before we add that second number, which is 3. So where does that 9 go? Well, it gets stored. And then when we hit the equal sign and the 12 is the result, well, we have to store that result of 12 as well. Okay, so all of these numbers require storage. So really what we're saying here is that this calculator example contains not only combinational circuits which form the addition in the adders, that's obvious, but the sequential circuits form the basis for storing those digits so that they can be reused. Okay, sequential circuits, as a summary, the important thing to note here is that they can store data, and the flip-flop can store exactly 1 bit of that data. They can store a 0 or they can store a 1. Now let's go back to that example we had in the first or second slide, which shows the feedback loops that are present. So you can see here from this example we've got this NAND gate and this NAND gate, and the output actually feeds back into the input of the other gate. Okay? We'll show you why that is an important characteristic of a flip-flop, but these flip-flops must have this feedback mechanism in all the circuits. That's how you can distinguish them from combinational circuits. There are four basic flip-flops we're going to look at. This one in front of us here on the right is the RS, and we're going to look at the clocked RS. Let's discuss some of the functions of the flip-flop, one of them being about timing. I'm going to introduce two terms here. One of them is asynchronous. Asynchronous means that outputs are not in time with some clock, and they change as soon as inputs change, which is what you see here on the right with this soccer game. The score is added to the scoreboard as soon as that ball goes in the net, and we don't really know when that ball is going to go in the net. It's random from game to game. A synchronous flip-flop, the outputs really are in time or synchronized with some sort of clock, much in the way that all of the devices and electronics and circuits that are contained on a motherboard on your computer are in time with the CPU clock speed. Okay, and those outputs only change on one of those clock pulses, regardless of what happens in between. Okay, and that would be like almost like a conductor that is controlling the time of a symphony orchestra, and those instruments are responding precisely to the timing which is dictated by that conductor. Okay, some of the functions of the flip-flop that we need to understand and introduce some terminology here. You can see this Q and Q naught, and those are very common terms used to describe the output of flip-flops, and those states are referred to as Q and Q naught. And you can probably guess that this Q being the normal input, that complementary, which is the Q naught, always has to be opposite. So if the Q is a 1, and then the Q naught, of course, has to be a 0. Likewise, if Q is 0, then the Q naught has to be a 1. And we're only going to run into difficulties when these two outputs are the same. So there are four different modes of operation which describe those output states. The first one we call the set state. Okay, and that set state refers to when the Q output is high, when it's a 1, which obviously means that that Q naught is a low. The reset state is when Q is low, or when Q naught is high. We call that the off or reset state. The next state is called the hold state, and again, this is describing the position of the output which is the same as the previous state. So whatever previous state was there, if it's the same after a change of inputs was made, then we call that the hold state. And the last state we call is the prohibited state. So we say that it's not legal or not allowed that these two inputs occur at the same time, resulting in outputs which result in these outputs Q and Q naught being the same. So for example, if Q and Q naught are both high, well, that's impossible because they're supposed to be opposite to one another. So we call those states prohibited. There are two ways we can build flip-flops. One is using logic gates, and I suppose there are three different ways if you wanted to build them right from transistors, but we will be using logic gates, and mostly we can use NOR gates, but we're going to be using NAND gates. And also we can use integrated circuits, and these integrated circuits are very useful, particularly if we're using them for a lot of flip-flops, and we'll actually be using these commercial flip-flops, commercial D flip-flops they're called. And this is an example of one here. You can see on this IC there are 14 pins, okay, and there is one flip-flop here and one flip-flop here. Here we have our RS flip-flop on the right expressed as two NAND gates with the corresponding truth table on the left. The truth table looks like it has quite a bit of information I'm going to go through with you, and then we'll look at the circuit itself. If I have two inputs which are S and R, here in this example 2 to the power of 2 gives me 4 possible combinations. So I have 0, 0, 0, 1, 1, 0, 1, 1. And likewise I have two outputs here, Q and Q naught. And you can see that over here on the logic diagram, S and R and Q naught. Now what's different is I've added these modes of operation which I've already gone through. The prohibited, set, reset, and hold. And you notice that On the other side here is it says there's a column I've added called the effect on output Q. So really it's just an expansion of what the mode of operation is on the left. So for example, you can see how with this prohibited state it's saying do not use, because the output is 1 for Q and Q naught is also 1. Well, you can't obviously have that as an output because they're supposed to be opposite. That's why it's prohibited, and we do not use those sets of inputs on an RS flip-flop for that very reason. That leaves us with 3 possibilities left. The set state, or set mode of operation, is when Q is high. And the way we achieve that is when we put S to 0 and R to 1. Likewise, the reset state is when we have Q is at 0, Q naught is at 1. And to accomplish that, S has to be 1, R has to be 0. And then the hold state, which is both inputs are 1, means that you get Q and Q naught are really result in whatever they were before. So if Q was a 1 before, and we were in the set state, and then we went to the hold state, we would just leave that state unchanged. It would still be Q. Likewise, if Q was 0 and we went to 1, 1, Q would still be 0 and we would be in what's called the hold state. So you really only have to worry about 3 different states. Well, let's look at this in greater detail. We know that this flip-flop, this RS flip-flop, is an asynchronous flip-flop because it doesn't have a clock. And secondly, what's really interesting about it is these feedback loops here that come from the output of this gate and feed into the input of this other gate can be confusing to look at, but I want to just clarify something for you. When you look at a NAND gate, when do you always get a 1 output? Think about that for a second. When do you always get a 1 output? Well, you would always get a 1 output whenever you have a 0 input. So what happens here is if we have a 0 input right here, then what will happen is you'll always get a 1 as an output, which then feeds into this other gate. And that creates a lot of the outputs that you'll see, particularly the set and reset state. When it's 1, 1, well, we're into that hold state, and that's why it doesn't change. This last slide illustrates the role of the RS flip-flop, but it does so in a symbolic way. So much like a NAND gate or an AND gate, that's the elongated D symbol that we've seen so many times with the flat back of the 2 inputs and the 1 output. This is the same principle. It's a symbol. It symbolizes what the circuit actually does rather than having to worry about gates. Okay, it's like a block diagram. So you notice that it has inputs, it has outputs, and whatever happens in the middle is like that black box theory of basically it represents the circuit itself. So you notice that the S and the R, okay, are here, and then the Q and the Q naught. Well, you should notice that the S and the R have inverted inputs. So you won't see this with any other flip-flop, only with this RS flip-flop. Well, I go over here, and if I look at the set state, S is 0 and R is 1. Now that's very unusual. Usually with all the other flip-flops, you'll notice the set state is when S is 1 and R is 0. And the reset state is when R is 1 and S is 0, which makes sense. But here, because we have these inverters, it actually inverts the result. So if you think about this 0 going in, this set 0, it would go through that inverter, and then it would actually come out as a 1, and that's what creates the set state. Okay, and that's all for this section of the flip-flops for RS flip-flops. We'll continue on later with another video series.